Now we'll be covering systems of equations and solving them by graphing. So we just did systems of inequalities, and you graphed them. You graphed multiple lines on the same graph, and you shaded. And the solution to the system of inequalities was the double shaded region. So there were lots and lots of solutions. You could choose any point in the entire double shaded region. A system of equations is now a set of more than one equation with the same variables. So just like with inequalities, it's going to be two or more equations now versus inequalities with the same variables. So the solution now to a system of equations is the point of intersection. So it is where the lines cross each other, where they meet. So a solution to a system of equations is only going to be that point. It is not going to be an entire shaded region. It's going to be one point, unless it's a special circumstance. So let's talk about that right now real quick. These are the possible solutions you could come up with. You could have two lines that cross each other, as these do. They would have one solution. Now your answer would not be one solution, it would be the actual point. So let's say this is at -2, 1. The solution would be the point -2, 1, and we would write it as a point. It is the point where the lines intersect, okay? In this case, we have parallel lines, and knowing the definition of parallel lines, we know that that means the lines never intersect. Well, if our solution is where they intersect, and they never intersect, we're going to have no solution. So if you have parallel lines, which remember, parallel lines have the same slope, so if you have two lines with the same slope that are therefore parallel, there will be no solution because there is no point of intersection. And the final possibility is that you have the same exact equation twice, meaning the lines are laying on top of each other. If the lines are laying on top of each other, this is a solution, this is a solution, this is a solution, this is a solution, this, and they go on forever. So there is infinitely many solutions. Infinitely many. Because I could pick any point that falls on that line and it would be a solution to that system of equations. Now this doesn't mean that every single point is a solution. The point 0, 0, that's not on the lines, so that is not a solution. But every point on that line, and because they go on forever, there's an infinite number of them, every point that falls on the lines that are laying on top of each other would be a solution. So three options. We can have one solution where the lines cross each other, the point of intersection. We have no solutions at all if the lines are parallel, or we could have infinitely many solutions if the lines are laying on top of each other. So let's talk about how we're going to do this. It's going to be very similar to how we solved inequalities, systems of inequalities by graphing, just slightly different. So to solve, first we're going to get all the equations in slope-intercept form. We know that we need them in y = mx plus b in order to graph. So first step, solve for y. Second step, you're going to graph the equations on one graph. So just like I did in these up here, you're going to graph all the lines in one coordinate grid. Then you're going to find where they intersect. The ordered pair or point where the lines cross is the solution. So it will be written as a point as we did right here. Open parentheses, the x value, the y value, close parentheses. Then, very cool thing about this, you can check them to make sure that you're right. If you take the x value and the y value back into both of the original equations, or all of them if there's more than two, it must make the equation true. So I would have to end up with something like 5 = 5, and if I did that for both equations, I would know that I had my answer correct. Okay? So solve for y, graph them, find where they intersect. Let's try a couple. All right, here is our first example. We have the line 2x plus y equals 6 and the line negative x plus y equals 3. First step is going to be to solve them for y. So I'm going to start with this one. To get y by itself, I subtract 2x from both sides. So y equals negative 2x plus 6. I know that in order to graph, I need the slope and the y-intercept. My slope here is negative 2. If you like to write that as negative 2 over 1, you may do that so that it's in the form of rise over run. My y-intercept is 6. And I can graph this line. So 1, 2, 3, 4, 5, 6. Here's the y-intercept. I plot that first. Going to rise 2, run 1 to the left. Okay. And then I'm going to draw my line in. All right, there's my first line. And now my second line is negative x plus y equals 3. I need to get y by itself, so I'm going to add x to both sides. I end up with y equals x plus 3. That gives me a slope of 1. You can write it as 1 over 1, and a y-intercept of 3. So I plot my y-intercept here. I rise and run the value of the slope starting at the y-intercept. So rise 1, run 1. Rise 1, run 1. And I draw my line in. The solution to the system of equations is the point of intersection. That means that this point right here is the only point that works in both of these equations. It is the only point that falls on both lines. And remember, you can check yourself, which is a very wise idea. So I'm just going to write this point out. So this is over 1 up 4. 1, 2, 3, 4. So 1, 4. So I'm saying that the solution is the point 1, 4. But I'm going to check myself before I submit that because I want to make sure I'm right. So I'm going to take this first equation, 2 times 1 plus 4, and we want to know, is that equal to 6? Well, 2 times 1 is 2, plus 4 is 6, so 6 equals 6. That is a true statement, so I know that this point falls on this line. In order for it to be the correct solution, it must fall in both lines, so let's check this one. Negative x, so that's going to be negative 1, plus 4, I want to know, is that equal to 3? Well, negative 1 plus 4 is 3. 3 equals 3. That is correct. Therefore, the point 1, 4 falls on this line. Because the point 1, 4 makes both equations true, it is the correct answer to this system of equations. Okay? So we, again, solve for y so that we have the equations that we can graph. Graph both lines, check for the point of intersection, and then check your work, make sure you're right. Okay? There's no shading involved with systems of equations. Let's try this next one. We have the line a equals 2x minus 2. I need the slope and the y-intercept. Excuse me. The slope here is 2. The y-intercept is negative 2. I'm going to plot that. Starting at the y-intercept is at negative 2. I'm going to rise 2, run 1, rise 2, run 1, and draw my line in. Okay. You got to be real careful graphing by hand. It would be very, very wise to use graph paper because if you get off even a little bit, it's hard to tell. So you got to be real careful when you're graphing by hand. Second equation is 3y plus 6x equals 18. Need to get y by itself, so I'm going to start by subtracting 6x from both sides. 3 3y equals negative 6x plus 18. My next step is going to be to divide everything by 3. Those cancel. That leaves me with y equals negative 6 divided by 3 is going to be negative 2x. 18 divided by 3 is going to be 6. That's a slope of negative 2 and a y-intercept of 6. Okay? So y-intercept 1, 2, 3, 4, 5, 6. And then I'm going to rise 2, run 1 to the left. Or go down 2, 1 to the right. And I'm going to do that slope a couple times because I wanted to make sure that it was in the right spot. It's very important that you graph them very accurately. Okay? So I can clearly see my point of intersection is here at 2, 2. 2, 2. Again, I'm going to check my work real quickly just to make sure that I have it right before I submit it. So y equals 2x minus 2. I wanted to plug them in. 2 equals 2 times 2 minus 2. 4 minus 2 equals 2. So I have 2 equals 2. So this point, 2, 2, is a solution to the first equation. Let's check the second one. 3 times 2 plus 6 times 2 equals 18. 3 times 2 is 6. 6 times 2 is 12. 6 plus 12 is 18. 18 equals 18, so I know that this point, 2, 2, is a point that falls on this line. Because the point 2, 2 makes both equations true, my solution is 2, 2. Okay? All right, let's do a couple more examples. Woo, dropping stuff. Here we go. First one, 2y equals x plus 4. 2y equals x plus 4. Got to get y by itself, so I'm going to divide by 2. Y equals 1/2 x plus 2. That's a slope of 1/2 and a y-intercept of 2. So I'm going to go ahead and graph that line. So here's my y-intercept. I'm going to rise 1, run 2. Rise 1, run 2. I'm going to draw that line in. And it's nice now because these are equations and everything's equal. I don't have to worry about dotted line or solid line because it's always going to be solid. Y plus 5 equals 1/2 x. I need y by itself, so I subtract 5 from both sides. Y equals 1/2 x minus 5. That's a 1/2 and a y-intercept of negative 5. 1, 2, 3, 4, 5. Rise 1, run 2. Rise 1, run 2. Draw my line in. And I see that these lines appear to be parallel, but I always double check. I know that parallel lines have the same slope. These lines do have the same slope, so what is the answer? The answer is not same slope. The answer is not parallel. The answer is no solutions. We want to know where do these lines cross, and they do not. So it is no solution. Okay, let's do one more, last one. We have negative 5y equals 10x plus 10. Need y by itself, so I'm going to divide through by negative 5. That gives me y equals 10 divided by negative 5 is negative 2x. 10 divided by 5 is negative 2. That's a slope of negative 2 and a y-intercept of negative 2. So I plot my y-intercept. Rise 2, rise 2, run 1, that's negative. Rise 2, run 1 to the left. This is not a point. rise 2, run 1 to the left. Okay, there we go. I have this line here. All right, now I'm going to do the other line. The other line is y equals negative 2x minus 2. That's a slope of negative 2, a y-intercept of negative 2. I plot it, same spot, rise 2, run 1. What do I see is happening here? My orange line is directly on top of my green line. That means there's an infinite number of places where these two lines are touching. Therefore, it's infinitely many solutions.